Hi there, I'm Matt Bishop. I'm the Managing Director at Brevity Digital. This here presentation is part of a workshop I'm doing next week on Monday for QuakeCore, and it's about the automation of earthquake engineering and how can we validate and trust automated engineering methods. This particular presentation quickly highlights some of the advantages and challenges of automated engineering methods and how we might deal with that. So, moving on. Specifically, I'm covering new opportunities for engineering automation, how LLMs like ChatGPT can be applied to engineering automation, introducing component-based engineering and what that is, giving an example of that through 1170.5 library that we have, look at the risks, benefits, and liabilities of automation, and introducing the standard contracts or licenses that are used for software. So this here is pretty much the step change in engineering automation potential from what we do now, which is very useful but also very complex Excel spreadsheets, to using something like Cursor, an AI development environment to create custom software, custom apps, integrate with modern databases and modern APIs. So to be able to use these tools, we need to learn new languages, like, for example, Python for engineering, back-end engineering methods, and JavaScript for front-end web apps. And within those two languages, I've just listed some of my favorite things there for Python and Jupyter Notebooks, TensorFlow for AI development, and then Matplotlib, SciPy, Pandas, Py9. Probably could have added NumPy there as well for using with Python. And in JavaScript, the same: React, Vue, Tailwind, and Flutter for making really good-looking web apps, and then Firebase and Azure as examples of modern databases. So lots of new words, lots of new languages to get used to. So this is the great thing, because this is what LLMs do really well. This is why that step change in automating engineering methods is available to us. An LLM can help us to translate our civil engineering language. And I say civil engineering, I mean all engineering that's not software engineering, and can translate our civil engineering language into software programming languages and interface between those two. It does it really well. Does that really well. What LLMs do not reliably do is carry out engineering analysis. Hey, ChatGPT, is this beam strong enough? It might give you the right answer, it might not too. It might give you the answer that you think you want to hear. I just want to make that distinction between using a large language model to translate between languages and using it to generate the actual analysis. Those are two separate things. LLMs, it's also worth noting that using an LLM in this manner is like using a sledgehammer to drive a nail. You've got a tool that has been developed for billions of dollars in a very complex way. The image there is of how the different layers of a neural network work to provide answers to create LLM models. And it takes an awful lot of code and an awful lot of time. And if we've got a comparative to a simple engineering problem like this one here, it's four lines of standard algorithmic-based code. Okay, so moving on a bit further, we have this ability to step change how we're doing our engineering methods, and that allows us an opportunity to move from common data environments, which is where the discussions are at the moment. That's like federated digital twins and things like that. How do we share information between companies, between regulators, between clients, to common execution frameworks, which is an idea that software has gotten hold of many years ago to create things like the Node.js environment, Node package managers, and the Python equivalents with PIP, to mean that you don't have to develop custom code for every project. You can use other people's libraries and bring things together to enhance your own project. Common execution framework in engineering would look a little bit like what we've done with our 1170 libraries. So, common data environment, how do we share the data? Common execution framework, how do we share our engineering methods? And essentially, it's like this. This is our publicly available open source standards function library. You can find it online, github.com, Constratum Engineering Standards. And that's a library of Python and Python functions and JSON database. And I've got a quick example of what that looks like for 1170.5, where you can see this. There's two equations there, two algorithms, one for the near fault factor, one for the floor height coefficient. Just picked a couple as examples. And then there's the database for Z factor, near fault distance, pin to latitude, longitude, and also with the regulatory environment there as well. So the cool thing about this is this is a open source shared library of the functions and data that is embedded in the standard, but it is not a shared version of the copyrighted standard itself. This is the intelligence within the standard that can be used across all of our programs or anybody's programs that wants to use it without violating the copyright that NZ Standards has for the actual standard. So shareability, obviously, is one thing that we get out of this, and standardization. But other benefits include modularity, being able to update a centralized library. We can update our 1170.5 library, and that propagates through all of the engineering methods that use it. Transparency, we can see through version control exactly when it was changed and who changed it. We can take that library and we can extend it, fork it to create something new. And the more we use these shared standardized libraries, the more consistent and compliant our practice is. There's risks as well, of course. Now, this here diagram is taken from a guideline document that the AI and AEC working group is working on, and essentially summarizing five key risks with using AI, specifically in AEC: intellectual property, confidentiality and privacy, accountability and care, liability and risk, transparency and disclosure. I'm going to look specifically at that question around liability. So we have our open source engineering methods or open source engineering standards libraries. Who's liable for when somebody uses those open source methods? So again, software has a great answer to this. They've been doing it for a long time. One of the most common open source licenses is the MIT license. And you can see that the MIT license basically gives anybody permission to use the software in any way that they want, distribute it, even sell it if that's what they want to do. But it's provided as is without any warranty, no liabilities for the authors or copyright holders. So all the risk is transferred to the person that uses the open source software. It's up to them to decide whether it's going to meet their requirements. So open source is one form of software development. Closed source proprietary being up at the other end, and an awful lot of things in the middle of that. I've had a look at how we answer that question, when is open source appropriate? And I've got a graph here which shows increasing commercial value from bottom to top and increasing professional value from left to right. And you can see that for various different cases, there's more commercial or more professional value. And just quickly, I'll go and look at, say, client relations. Our CRM database has great commercial value to our firm. It's all our clients, all our relationships, all our deals. We keep that proprietary. On the other end of things, we keep it proprietary, high commercial value, low professional value. On the other end, engineering methods and standards have some commercial value, but the professional value of making sure that our methods and standards are correct pretty much outweighs the commercial value we get from holding that proprietary. So we're happy to share our engineering standards as open source. And then as an example on the far end, considerable professional value in a doctoral thesis, but you'll really struggle to sell your thesis directly to a client. So very little commercial value in that actual information, and of course, they're all publicly available too. If you cross that over with the standard licenses, you can see that the MIT license is great for a high professional, low commercial value software, and then closed proprietary software at the other end. And then there are various other licenses that give you certain amounts of control around what it's used for, like CC by NC allows academic use but restricts commercial use. And this might be a great license to use for peer review, say. You want somebody to be able to look at what you've done, but you don't want them to use it on your next project. Now, we are doing top end and bottom end. Some of our software is closed if it's got high IP value, and then some of our software is open. We haven't really worried about the bits in the middle. And that ends my presentation for today. As always, if you have any questions or thoughts, reach out. I'll be happy to discuss with you. See you later.